Okay, great. Okay, so it's a pleasure to have Azadeh Farzan with us today to deliver this verification seminar talk. So Azadeh is a professor at University of Toronto, and before that she did her PhD at UIUC, and I think also a postdoc at CMU. Azadeh is very well known, I think, for her work across various topics and in formal methods, programming languages, especially verification, synthesis, testing, and particularly all these three for concurrent programs. And, so today she'll be telling us about some of her recent work in, I think, this year's POPL, in equivalences for causal concurrency. So welcome, Azadeh, and over to you.
Thank you so much. Thanks for the introduction and for having me here. This is, in some sense, part of an ongoing work that we started with Omeng a couple of years back when we were both in this program at Simons that was a little doomed because of the pandemic. It basically had to move online and none of us could actually be there. But it was fruitful for us because this work eventually came out of that program. So without kind of beating around the bush too much, let me try to break the title down for you. I would talk about equivalences on program runs and what they mean in the context of dynamic analysis, and what causal concurrency is, so that we set up precisely what problem we are trying to solve without any delay. So let's start with equivalences. I wouldn't kind of insult anyone with defining what an equivalence relation is. That's kind of the classic mathematical definition. But in almost any context that an equivalence relation on program runs is used, there is a concept of soundness that we really care about. And I'm using the term soundness, but in reality, you should interpret this in this particular context as usefulness, really. So we say that an equivalence relation on program runs is sound if whenever we pick any run in that equivalence relation and it is actually a valid run of the program that we care about, the program that it comes from, then any other run that is declared to be equivalent to it is also a valid run of the program, and it produces the same outcome. And I understand that the same outcome may not be precise enough for people, but I would kind of suggest that you let that part go, because it's not really the goal. It's really the thing that serves us the actual goal. And the part that we really care about is that the equivalent run is also provably a valid run of the same program. This is really the key thing that we care about with equivalence relations in this particular context. All of this will become clearer and clearer as we go. Let's, for a second, just leave it at that. And turn our attention to, okay, let's say we have such an equivalence relation. What is its point in the context of dynamic analysis, which is the topic of this talk? The point is that with dynamic analysis, usually our observation of the program is limited to its observed behaviors or its runs that we see. And the idea is that, we see very little of the program in a single run. So if we are trying to check for some behavior, look for bugs, things like that, a single run seems like such little exposure to the program. And over the years, an array of techniques have been developed that basically say, okay, I observed one run, I'm going to use the notion of equivalence, that is sound, that I just mentioned, to sort of speculate that other than the run that I've observed, there are all these other runs that belong to the same program. And rather than just, in a sense, test or check one run at a time, I will basically test a bunch and give myself more chances of exposing something wrong from the program rather than I would see from a single run. So you see now already why I mentioned that the key is I want all the runs that I declare equivalent to be the runs of the same program, because if that's not the case and I detect something bad, I may be raising a false alarm for the programmer, because I kind of say that there is a problem with the program in a behavior that doesn't actually belong to the program. Now, let's turn our attention to the other side. When we say we want to check for something or test for something, what are these things? So there can be many things. This talk specifically focuses on this key decision problem, which is called causal concurrency. It's a very simple problem. It's kind of arguably the simplest kind of question that I can ask about a run. Very elementary, but at the same time, very powerful. So we say that two atomic steps observed in a program run are causally ordered if they appear in the same order in every member of the equivalence class of the run. So in some sense, we are saying that it matters that they should be in the same order. And if I change the order, in some sense, I may be stepping outside a set of equivalent behaviors. And of course, if two atomic steps are not declared causally ordered, they would be declared the dual notion. They're complementary. They're called causally concurrent, which means that their respective order does not really impact the behavior of the run, the outcome of the run. So they can be kind of called causally concurrent. So if I had an oracle that would be able to answer questions like this about a program run, basically looking at its equivalence class, then I would be able to do a bunch of different types of testing, or predictive testing, more importantly, for concurrent programs. So, for example, I'm hoping everyone is familiar with what a data race is in a concurrent program. So you can have two accesses from two different threads. At least one of them is a write that can happen simultaneously. That's called a data race. Now I can observe a program run, and it's very, very unlikely that I see actual simultaneity of two problematic accesses at the same time. It can happen, but it's a very rare event. But I may see the accesses kind of far apart from each other. But if I ask my causal concurrency oracle, are these reorderable or are they strictly ordered? And if the answer is they are reorderable, then I can speculate that there exists an equivalent run in which they would actually happen simultaneously. So as such, predict a data race. So this is one example. You can think about others. For example, you can kind of think about a category of errors that are called order violations, that say that whenever you have an initialization of a variable and a usage of it, the initialization should always come before the usage. Otherwise, there's a problem with the program. So there are not everything that we are interested in, but there are a lot of things that sort of rely on this core decision procedure. So as such, we decided to focus on this core decision procedure and study it in the context of equivalence classes on concurrent program runs. So that's more or less the clean setup of the problem that I want to discuss today. Now, of course, once we know causal concurrency is our problem and we want to look at it in the context of equivalence classes, and soundness is important to us, the natural question that comes up is, what is the largest sound equivalence relation? So you kind of can see instinctively that the more behaviors I can declare equivalence, the more prediction power I'm giving to my oracle. So I'm in some sense interested in the largest such relation with the maximum prediction power. And this is something that has been studied in the field before. There is a notion of reads from equivalence that I think was super cleanly studied with Parosh, Abdullah, and the company in 2019, but I think like bits and pieces from it appeared in earlier work as well. And to sort of define this, rather than generically think about concurrent program behaviors, we have to set down a particular alphabet of actions for programs. And this is, in a sense, the most classic one, in which you observe atomic steps of a program run to be what thread is making what sort of operation, memory operation, to what shared variable. So any event would kind of say a thread like T1 performed a write to a shared variable X, or a thread like T2 performed a read from the shared variable Y. And if we set ourselves at this exact power of observation, then we can define the largest sound equivalence relation on concurrent program behaviors like this. So it's called the reads from equivalence, and says that two program runs are equivalent, or reads from equivalent, if and only if they execute the same steps from the same threads in the same order. So really, the part that says the same order is rather easy. You just want to make sure that you don't change the order of actions within each thread. The part that says that it's the same steps is a little more tricky. It kind of cannot be enforced just there, which motivates the next condition, which says we want to maintain the relationship between reads and the writes that they observe in every program run. So any member of the equivalence class, every read should always read from the same write that it reads from in every other member of the equivalence class. So if you think about this for a second, you would sort of understand that by fixing this, we are basically making sure that the behavior of the program always remains the same. And as such, even if the program is branching, looping, all this structure that is in runtime really invisible to us, as long as we make sure that this association stays, we can conclude that the reads would read the same variables, and therefore they would follow the same program paths based on branching, looping, whatever kind of depends on the value, we basically execute the same way. So the combination of these two guarantees that everything that I will call reads from equivalent is going to be a behavior of the same program producing the same outcome, exactly what I called soundness earlier in this talk. So just to see an example for this to kind of click visually in everyone's kind of mind, you see two kind of behaviors on left and right. The details are really not important. You can really think about the pink arrows as making sure that within each thread, the order is never broken. So it has to be, the pink arrows have to be maintained. And the blue arrows are exactly the matching of the reads and the writes that they read from. And you can move things around that, but as long as that blue arrow remains and the matching right for the read doesn't change, we would call these two runs equivalent. Okay, so it is this relation that is defined this way is in fact the coarsest sound equivalence relation on program runs. And I want to kind of emphasize the fact that it would be the coarsest if we fix that what we observe from the run, all the information that we have from the run is coming exactly from the alphabet that you see on top of the slide. So, for example, people have looked at variations.
Can I ask a question?
Yes, please.
In the previous slide, are the two writes, the initial writes to X, are they assumed to write the same value? Because they moved from one thread to the other. Yeah.
So you're talking about when you say previous slide, you mean the example that I showed, this one?
Yes, yes, sir, yes. So are the two W
Right.
of X's assumed to write the same value because they're in different threads?
So it's an interesting question, but I want to emphasize that in this example, the answer doesn't matter because there is no read on either side that actually reads an uninitialized value.
Okay.
Does that make sense?
Yeah, in general, but
in general, there are a lot of ways of cleaning things. So for example, if there are reads that start and read from uninitialized values, people kind of assume that there are this set of writes at the beginning that write those uninitialized values, and you go back to this sort of clean scheme in which you don't need to have considerations for this. Does that make sense?
Okay.
Okay. Right. So you can kind of like do the reasoning in your head a little bit that if you break any of the two conditions that I put up there, Not that it's guaranteed that you will not get another run of the program, but you can always make it adversarial so that if you break one of these two conditions by, for example, making a read essential to a branch, that if it reads a different value, then the program would go a different way, that if you break them, you no longer have the guarantee that you will get another run of the same program. So that is, in a sense, the intuition behind this is the coarsest relation that you can define that would be sound. And by the virtue of this being the coarsest relation, any other sound relation that anyone ever wants to invent and work with would be a refinement of this relation. And you can kind of think about any relation that you have, you want to talk about its soundness, you just basically prove that it's refining this relation and as such is sound. Okay, so if this is the coarsest relation, it gives us the most power in prediction. Let's look at the complexity of deciding causal concurrency based on this. If all is well, we don't even need anything else. This is the best relation we can get. If we have an algorithm that works well in the time and space that we like it to work in, then we're done. There is nothing further to discuss. But we studied the complexity of this problem, and it turned out that things are not really as well as we would like them to be. The most important sort of complexity result is this lower bound that says that if you wanted to check for causal concurrency in a streaming fashion, as in as you're reading the concurrent program run from left to right and sort of trying to decide on the go, then you require a strictly linear space to make the causal concurrency decisions. And this is really the most important, in some sense, bad thing that we care about. But let me just briefly mention a bunch of other results that I will not get into that we studied. So for example, we can just say that, okay, the lower bound is linear space, but linear space is enough. So we can actually decide in deterministic linear space causal concurrency. Then we studied that, okay, is there some tension between time and space, that if you kind of give up on one, get something on the other. And there is this kind of idea that you have a quadratic time-space lower bound. So if you try to kind of reduce one, you have to compensate with increasing the other. And finally, the complexity of deciding this in time sort of corresponds exponentially on the number of threads. And this kind of gives me an in to explain something that if you're not deep into this space, you would be a little bit confused about. And that is, in this space, for whatever reason, it's been decided that the length of a run is a variable, is a value that is always far, far, far greater than the number of threads and the number of shared variables. Therefore, a lot of complexity results are always considering the length of the run to be the only variable and the number of shared variables and the number of threads to be constants. So in some sense, there is no contradiction between what you see at the end and what I said at the beginning. All the linear space lower bound is really talking about that you need at least linear space on the length of the run. And the rest of the results are considering the number of the variables and the number of threads to be constants, with exactly this view that you may have in a program 10 threads, 15 threads, 20 threads, but the length of the run would be in the millions, possibly in some cases even billions of events. Did I hear like something like a question or? Okay. All right. So, but
So actually,
really,
there is a question, Azadeh, from Gautam. Gautam, if you're there, can you go ahead and ask it? So let me read it out. He says, I think I might be misunderstanding something. What if we had an equivalence where the second condition is weakened to only require that each write reads the same value from whichever read that it reads from?
that's exactly my point about all of this kind of relies on what you set as your power of observation. And my power of observation is I see which thread performed which action, read or write of a shared variable. I don't have access to that information. I don't have access to values, but I can change the alphabet of action and see the values as well. And then I would have an extra bit of wiggle room to say that I don't have to match the same write, I have to match to a write that sees the same value. But this kind of, in this context, we're sticking with this. The other one is sort of not as well studied or well known or well liked. And I can't really tell you what the details are for why that is. It's been studied a little bit, but somehow reads from equivalence with the alphabet that I showed you and the power of observation that I showed you is really the key thing that most people care about. Please go ahead, Dhruv, if I'm pronouncing this correctly. I'm sorry, I'm not.
Yeah, you are. So I had one question, and maybe I'm just trying to understand the setup of the whole problem. So deciding causal concurrency means that you're given a program, you're given two labels, which are two actions.
Exactly.
And you want to check whether in every execution alpha and beta are, let's say those are the two constants labels.
In every equivalent, equivalent run.
In every equivalence class, they are causally concurrent.
Yeah.
But I don't understand how we can decide this in a streaming fashion because we have.
It will come. It will come. Bear with me.
Okay,
I will not really talk about this one that is bad. But you know, it's just basically it's an uninteresting algorithm. Yeah, because there is you just basically are remembering everything and dealing with it. But I'll give you examples of streaming fashions for cases that it is a little easier.
So, so if I'm right, it's potentially causally concurrent, not definitely causally concurrent.
No. It is definite. The answer is always definite. Definitely ordered, definitely concurrent. And I want to kind of maybe your instincts are right, and I want to kind of interpret the linear space lower bound as effectively the algorithm has to remember. Actually, let me flash an example, and if you still have questions, ask me again, okay? Because it's coming sort of a little bit of intuition. So the most kind of bad news on the slide that you saw is this linear space lower bound, right? The linear space lower bound effectively saying that the algorithm has to remember the entire run to make a decision. And once you give it the power to remember the entire run, streaming fashion is really not a streaming fashion anymore because the entire run is in the memory of the algorithm, okay? And not to give you a proof, because it would take probably 15 minutes for me to go through a whole proof, and it's a little complicated and it wouldn't click. I'll kind of flash the idea of the proof using an example for you. So the run that you see on the left of the screen is something with two threads, and the two events that are highlighted that kind of with intent are appearing right next to each other to kind of make this the most dramatic possible are the ones that we want to query about whether they can be reordered or not. That read X and that write X, okay? And the answer to whether they can be reordered or not is yes, they can be reordered. And the run that you see on the right is a reads from equivalent run in which they have been reordered. But for me to be able to make this decision, I really don't have much wiggle room rather than remember the entire run in the left and transform it more or less only to the entire run on the right. So if you start to kind of look at all the implied dependencies or orders by the ones that are already marked, which are the thread order using the dotted lines, and the blue arrows are exactly these matching reads and writes that have to maintain their order and their kind of matching relation. All the other red arrows that you see would be implied by this, and you will see that in the run on the right, you really have very little wiggle room. You may have a little bit of power to move the write X and the read X on the right thread, a little bit, a few events up and down, but more or less for you to make this argument, you would have to remember the entire left run and as a whole transform it to the one in the right. And effectively, the proof sort of builds on this pattern by creating this sort of arbitrary nested patterns of these blue arrows that you see on the left and the things that you see on the right to argue that for any length n, you really have to remember this entire pattern to be able to declare whether you can go to the right. And if one piece is missing, you wouldn't be able to do this. So it's not a super precise scientific statement, but it's a good kind of intuitive statement that this is hard because you cannot really break this transformation down into smaller steps. The transformation is a one go from left to right, and it requires you to remember everything. It's global reasoning and requires to remember everything in the run and then transform it. And as such, you need this linear space lower bound. Go ahead.
So, Azadeh, sorry, a question.
Sure.
So it's enough to just move the events on the second thread just, one up so that the WX comes before the RX. Right?
Then
that
you
should be
will,
sufficient, right?
So that, you see my pointer, right?
Yeah.
So this read X is matched to this write X, and you cannot change that matching in any equivalent run.
Right. No, I'm just moving the events in the right thread.
If you move
T2.
this up, then this read X would see this value. So it's no longer an equivalent run based on the definition that we had.
Oh, so the read has to see the last write, is it?
The read has to see the same write. So if you look here, this read
in the reordering. I thought you just have to see the same. Okay, I see. So the read has to see the last write. That is fixed.
The read always sees the last write. That is just basic sequential consistency.
Okay.
But what we are saying is that the blue arrows that you see in this have to be preserved in every equivalence run. And I'm calling the run on the right equivalent because you have precisely the same set of blue arrows.
I see.
And if it changes, for example, if this read now sees this write based on your reordering, it could be that write writes a different value, this reads a different value, and the program goes
then that would not be equivalent. Right.
Yeah.
So I had a almost related question. So are we assuming that we can observe a total order of the actions across both the threads?
We are observing the run as it comes, except that the run has been, every event has been tagged with the particular thread. So I've kind of visually illustrated for you this, but you could really think of this as you see T1 does this, T1 does this, T1 does this, and then T2 does this, T2. So this picture is basically constructed.
Are we told that the yellow R of X precedes the yellow W of X?
Yes, you will see them appearing in that order in the input run. So
it's a total order. It's a total order. Yeah.
Yes, it is a total. Yes, every program run by definition is a word in the language of the alphabet, which is a total order on the actual, events that appear in it.
Okay, thank you.
Sure. Okay.
So, Azadeh, sorry, one more question.
Yes.
On that same figure. So it's, so isn't it basically a partial order that, somehow aren't you asking, can I just get another partial order?
So you're absolutely right that you can think of it as a partial order, and you can kind of think algorithmically about solutions in that direction as well, except the partial order, the computation of partial order would basically require as much effort as solving the causal concurrency question. So for example, think about the red arrows that I have here, okay? Those are the extra arrows that actually complete your partial order and would let you make these kind of decisions. So I see the blue arrows and I see the thread order, and this one is a thread order. There's nothing special about it. But this arrow, think about the arrow between right T and right T. There is really no reason that these two have to be ordered, right? The reason that these two are ordered in here is because I cannot push this down here, because then this read is going to be matched with that write instead of this write. right? So in a sense, for you algorithmically to put the effort to infer these red edges is the same as making the decision, the same as making the decisions that you're trying to make in the first place. So you would not make your life easier by going that way. You will just basically make it harder.
Mhm.
And the thing that is actually making this difficult compared to other classic partial orders that I will get to is exactly this. These inferred edges cannot be inferred locally. It needs exactly the same global reasoning that I'm mentioning here to infer them and then decide based on partial order. But if the partial order would drop out of the sky for you, then it's going to be an easy problem. Okay, so this problem hard based on this particular coarsest equivalence relation. So that kind of begs the question, okay, linear on the length of the run bad because in a monitoring context in which we want really low overhead and the runs could be really, really long, I don't want an algorithm to have this much overhead of remembering the entire run and doing global reasoning over it to answer a really kind of simple query such as 2 events can be reordered or they cannot be reordered. So this gets me back to something that effectively came before this, because the hardness result that gave you was our sort of contribution, but it's been known forever, but somehow it's been a folklore result that if you stick to a classic equivalence that is based on commutativity, this is Mazurkiewicz traces and the notion of Mazurkiewicz equivalence, then you can actually do this in an easy way. So for people who may not have any background in this, here is a very, very flash intro that if you have a symmetric anti-reflexive relation, which we call independence or commutativity on individual actions that appear in program runs, then it immediately gives you an equivalence relation. How? So you see now the same 2 runs and you see that alpha and beta commute, and I can start kind of swapping commuting actions. So this one would be equivalent to the one in the top, and this one would also be equivalent to it, and this one would be equivalent to it. So you have naturally this induced equivalence relation that says that everything that is reachable within whatever number of swaps of commutative actions is equivalent to the original run. Now, when is such an equivalence sound? When it refines the reads from equivalence, which is the coarsest relation. And for that, we have to make sure that any swap will not break reads from equivalence. And there comes the 2 relations that a lot of people instinctively would buy. One is you cannot reorder events from the same threads. So those will never commute. And the other one is that you can never reorder 2 events that are events of the same, that are accessing the same shared variable, and at least one of them is a write. Because if you were to make such a swap, then you are risking changing the matching write for a read. And as such, you're not permitted those swaps either. And as long as you stop swaps of this kind happening, then any swaps that you make will preserve the reads from equivalence. They will preserve the thread order and they will preserve the matching writes to every read. And therefore, it's a provably sound equivalence relation as such. And if we were, and I wanted to kind of make a remark that the moment you set your sight on, I will operate at the commutativity level of individual actions from the threads, this is the best you can do. You need these conditions not to break reads from equivalence, and this is the most liberal you can be with the swaps, right? There isn't, if you go more liberal, you will risk soundness. So based on this notion of equivalence, now you can have a true streaming, constant memory way of checking for causal concurrency. And I can just this is in some sense known result, but this is folklore. No one can really know who for the first time really exactly mentioned this. I'll give you a very simple algorithm, not the best one and not the only one. So using an example. So imagine you have an alphabet A, B, C, D, because it's easier to fit a long word on this alphabet rather than the original on a slide. And imagine that the 3 pairs that I'm putting there are the commuting pairs. But of course, commuting pairs are symmetric. They would kind of commute in both directions. So a streaming algorithm basically is trying to decide whether the blue A and the blue B can be reordered. It will ignore everything before it sees the first one, the blue A. And at that point, it actually the algorithm kicks into action. And it maintains this memory that is basically keeping a set of alphabet letters that it has seen that are dependent on the source event, which is the blue A in this case. So when I see the blue A, the answer is just the blue A. It depends on itself. So I will keep that. Then I move on to the next event, and it's a B. And because B and A are independent, they commute, I have no updates to make to this set. I haven't seen anything new that depends on this. I will move on. Then I see the C. Now C is actually dependent on A. It doesn't commute against A. And I observe that, this C would be actually ordered with respect to that A, and I will add it to this set. Then I see the D, same story. D and A are not commuting. It will get added to this. Then I see another C, and I would want to add this, but I will realize that there is really no novelty to another C. I already have a C, and it suffices for all my future decisions, anything that would get connected to A through a C to get connected to the earlier C or the later C. I don't really need another C. So this set stays exactly as it is. Another C, the same. I will see the B because this B is a different kind of check than the earlier B. But because B is independent of all the 3 letters that you see there, A, C, and D, still B does not get added to this set. And I can continue processing the things until I get to the last B. And then my query is, all the letters that you have seen that depend on your source event, is this event dependent on any of them? And in this case, the answer is no. So we declare the blue A and the blue B to be actually causally concurrent. If the answer at any point would if this wasn't the blue B, if it were like a blue D, I would have immediately issued a verdict of ordered. So the trick really is that the size of this set that I need to keep as a memory of this streaming algorithm is bounded by the alphabet size and has nothing to do with how many events actually appear, how far away from each other the blue A and the blue B are. And that is exactly the thing that makes this decision problem easy. First, I really don't need to consider anything before the blue A and after the blue B. And in the middle of these two, the memory that I need to maintain is just really a bounded size snapshot of what I have seen and not the entire piece of run that I've seen between A and B. Okay. Now, this sort of presented us with this picture of sort of folklore told us commutativity-based equivalence is easy. We proved that doing the same thing based on reads from equivalence is hard, which sort of naturally asks the question, that's the largest sound relation you can have, and this is a sound relation that people have worked with in the past. We know we cannot relax those commutativity relation any longer, anymore, because we would lose soundness. So there is no wiggle room with that definition alone. Can we actually find another point, another equivalence relation that is sound in between these two that would still have the good algorithmic properties of the easy commutativity-based equivalence? And the answer presented itself in an observation that you can sort of keep it easy by keeping it commutativity-based, but you now extend commutativity from individual atomic actions that appear in the run to sequences of atomic actions, which I'm calling blocks. So we define the concept of what we call a grain, which is, at the moment, a contiguous sequence of atomic program steps. So, for example, if you classically would look at this read X and this write X, you would realize that based on standard commutativity, they cannot be reordered because they're dependent. It was part of the conditions that we said would preserve soundness. But if I look at the entire two grains that are marked with blue on the picture. Now the two grains can be reordered, and as such, they can kind of issue a verdict for me that the two yellow highlighted events that you see here are actually reorderable, which is something that classic commutativity, Mazurkiewicz commutativity-based equivalence would not permit me to do. So I want to make a quick kind of remark that even though this picture is simple, in general, a grain is truly a contiguous sequence of atomic program steps. There is no kind of sticking within the boundaries of a thread. So you pick your sequence anywhere in your run, and as such, a grain can sprawl over multiple threads. So this is a grain that you see going over threads T1 and T2, and the other one, a grain that is just in thread T3.
So, Azadeh, what is the atomic program step? I mean, when
These
you
are
say
exactly these reads and writes. If you remember, let me flash this for you quickly.
Okay, so contiguous means any contiguous on the total order.
In the total order, exactly. Yeah.
Okay.
So now I want to kind of tell you little by little, the moment we take this view, how can this now be a new notion of equivalence, which can be actually algorithmically checked easily, okay? So first observation is a very classic language theoretic one, that if you make a particular choice of grains, like the ones that are marked in this figure, then you can, up to a homomorphism, pretend that these grains, I mean, I guess classically in language theory, this is something that would call inverse homomorphism, but mathematically a homomorphism, nevertheless. You can kind of pretend that these choices of grains are effectively new letters in a new alphabet. So I can pretend that that first grain on the thread is a new letter A. The second one is a new letter B. The third one would be the same exact letter A, because really, all I really care about from a grain is what variables the grain touches, what threads the grain touches, and what is the nature of the access to those variables. So the first and the third grain are having the same kind of access to X, both read and write, and touch the same thread. So in some sense, I want to now emphasize that even though a classic homomorphism would match these words or subwords to actual letters, and then you would have an unbounded alphabet on your hands on the right, a simple observation that we really don't care about the nature of the letter to decide whether two grains would commute or not. We really care about the nature of the resources that it touches, then we have ourselves actually a bounded alphabet as a result, right? We call this kind of objects that you see summarizing these grain signatures, and these grain signatures are bounded by how much busy you can get talking about different threads and different variables. And once you have them, you can look at them and you can decide what letters of alphabet actually commute. So looking at this, we can say that, oh, B commutes against both A and C because it doesn't touch the same threads or the same variables in a bad way. For example, the two A's do not commute against each other because thread order forces us to keep their order. And A and C do not commute against each other because the thread order of T1 forces us to keep their order. So you can kind of have this mapping into a new alphabet, into a new kind of commutativity relation implied by that alphabet, which is finite, right? And now you exactly decide here about causal concurrency, as you would do with the classic alphabet that I showed you before. The problem is not different because I switched my alphabet. It is still classic Mazurkiewicz, just over a new alphabet. So I can make this decision with a single choice of grains. But of course, I don't want to be limited to a single choice of grains. So I want to define this equivalence relation, and I intentionally put a star there that will become clear in 2 seconds why there is a star. That I want to define it as two words are equivalent if there exists a choice of grains that says they are equivalent up to that choice of grains. Okay, so now I'm kind of giving myself the power to try out all possible choices of grains with the hope that one of them will actually get me from where I am to where I would really like to be. In a sense, I'm giving myself the most prediction power this way. So it's important to make an observation that exactly for the homomorphism reasoning that I did, for any particular choice of grains, up to homomorphism, we are exactly in the same domain that we were. So this relation is an equivalence relation, like Mazurkiewicz equivalence. But if I kind of now go over all possible choices of grain, this relation is no longer an equivalence relation. That's why I put a star there to emphasize this. It is symmetric and reflexive, but it is not transitive, precisely because you can go from somewhere to somewhere else with one choice of grains, and from there to somewhere else with a different choice of grains. But if you were to kind of But this second choice of grains may not present itself always where you want to be, right? It may present itself in the original source run, but after you make a choice of grains and make some moves, those choices of contiguous grains have disappeared from the resulting run. So there is this kind of a little bit of mess here that will make us not be mathematically cleanly where we were before, but it really doesn't matter to the particular problem context that we are, because this quote unquote, no longer a mathematical equivalence relation, is still taking a program run for me, and is in some sense defining a cone of influence or equivalence around it that are all provably sound, as in we know that they're all provably an equivalent run of the program, and I can basically do my predictive testing over it if I can make it algorithmically happen, okay? And I can make it algorithmically happen because I can just say that, okay, optimal homomorphism, we said that we can really pretend that we are back in the Mazurkiewicz realm. And we know the language theoretic trick that lets us use non-determinism or leverage non-determinism to make all possible choices of grains. We can just basically guess grains, and every time that we guess grains, we find ourselves up to this homomorphism in the realm of deciding, exactly as I showed you before, whether up to that particular choice, two things are ordered or concurrent. And we just decide to call two things concurrent if at least one choice says they're concurrent, and ordered only if all choices basically declare it ordered. So this simple tricks would let me use in a sense, invent an equivalence that is strictly larger than Mazurkiewicz, because Mazurkiewicz, which is basically guessing grains as individual events, is just one of the many choices that I have. And it will be sound, and it can algorithmically be decided in the same single pass constant time algorithm. Okay.
So sorry, Azadeh, so what is the equivalence that you're proposing now? Maybe I missed that. It's not the grain, not the grain equivalence.
It's this one.
Okay, but you said this is not an equivalence.
Yes, but in a sense, I have no option I cannot invent a new term for this half equivalence. So I put a star here to be able to, like, easy in English, keep calling it equivalence, but it really is not. You can kind of, call it a cone or whatever, you're more comfortable with. But rather than trying to invent a weird word, I decided to kind of acknowledge that it is not, but keep calling it an equivalence. But I'm not using any properties of, specifically the transitivity of it as an equivalence relation. So I'm safe.
Okay, but I thought your original problem statement required it to be an equivalence. That's not. That's not.
It really does not.
Okay.
It really does not require the transitivity of an equivalence relation. This is really the key.
Okay. And so also, if two things are grain equivalent, then are they also reads equivalent?
Exactly. Yes. Okay. They are. I sort of went a little, too quickly here and missed this. I want to make this remark here that the soundness of this, which is exactly the fact that it refines read from equivalence, comes from the fact that, for each choice of grains, you would make sure that you're sound, and I'm getting to this in a second. And then this being sound is just implied by the soundness of for all choices of G, this thing is sound. And this is effectively just the union of those equivalence classes.
Okay.
So you're only declaring things to be equivalent that are equivalent up to a sound choice.
Mhm.
So about soundness specifically, actually, I wanted to kind of give you this big picture first, because it's, going into the details of this, especially for anyone who understands basic automata theory, is just tedious and boring. But get to the more interesting part second, which is when I showed you this picture and I kind of told you, oh, if we choose these grains, then we can kind of argue that these two commute. I was waving my hands and I was being imprecise and I was lying to you a little bit. So I can do this, but it really matters what appears afterwards here. So for example, if these two grains are immediately followed by a read of X, it's not really relevant that this read is in thread 1 or thread 2. It really doesn't matter. It could be anywhere. Then you can see that if I were to reorder these two grains, I will be changing the write from which this last read reads. At the moment, it's seeing this write, and if I were to reorder them, then it would see that write. So this would be obviously not sound to do, which means that my hand wavy thing of you will kind of decide when you make two grains, you will decide whether they commute or not like this was imprecise. It actually matters what appears here. So if there is a read, I cannot do this. If there is a write, right after this, before I see any reads, not right after, but before I see any reads, then I'm completely within my rights to declare the two blue grains commutative. And this points out to the fact that unlike Mazurkiewicz commutativity, which we discussed, that you just look at the two events, you don't really need to consider anything else, just those two events, and you declare whether the two commute or not. With the grains, the commutativity of the grains sort of depend on the right context of where they appear in. And this immediately kind of sends alarms in everyone's minds. This sort of contextual dependence on commutativity is a recipe for disaster, really. But it just turns out that it looks worse than it actually is. So I wanted to first make a simple observation that if I wanted to just say that, okay, I'm going to kind of like brush over this problem by saying, I'm going to only declare two events commutative if they commute in all contexts, then I'm effectively giving up the entire power that I would gain from grain commutativity, because two grains would commute in all contexts only if their individual steps would Mazurkiewicz commute. There is no extra commutativity I'm going to get out of this. So for example, because I'm doing all contexts, I have to always declare these two blue grains non-commutative. So I will basically lose anything. What I want is not this, but be able to say that on the left, they commute, and on the right, they won't commute. And here, I can kind of make an observation that I can sort of make a guess, again, using non-determinism, that these two grains are going to be right, and they're going to see the appropriate right context. And as I then move on ahead, I will check and verify that that guess was actually okay. And sort of I'm adding this business of the right context to my guessing as well. And maybe if one thinks about this super plainly, one kind of says, wait a minute, there are unboundedly many right contexts. So maybe then we're dealing with unboundedly many commutativity relations. But it's really not so. So for example, coming back to this example that I showed you before, here, you can just say that I just decided non-deterministically to choose this grain. And really, I face two choices here. That this grain is kind of catching all the reads that see this right already. And therefore, I can make a choice that this will commute against all other such grains in the future or not. So I have these two choices. And once I make the guess that, oh, this grain is okay, it will commute the way that I want it in the future, I can kind of then make the same guess about this one. Specifically when I see that right, before I see any other read, my kind of guess gets verified immediately, right? It says that there are no kind of pending reads that are going to kind of create trouble for the commutativity of this grain, the guess is verified. If on the other hand, I see a read where I don't expect it to see, I basically kill that particular non-deterministic choice and not let it actually yield any results for me. So this kind of works implicitly based on this idea that we always want maximum commutativity anyway, and choosing that this commutes is opting for maximum commutativity if we make the right choice, and choosing that it doesn't commute is opting for, what if the other choice is wrong? So I'm going to have a choice of this not commuting as well. And I don't really need to consider any other kind of combinations. So with this sort of view in mind, I can revise what I showed you before, that when I'm guessing all non-deterministic choices of events, I also make all choices of this sort of maximal commutativity relations for both options, commute or not commute, and let the monitor verify with each guess that the things that appeared in the future were consistent with that particular guess. And I'm back into kind of convincing you, hopefully, without getting into too many kind of tedious details, that now I can guess and verify sound commutativity relations on grains that are contextual and give me the extra power of commutativity that I would wish I have in this particular context. Let me pause here and see whether there are any questions, because I want to now talk about the next level in this game. So close the topic on this and move on to something else. Any questions up to this point?
There are a couple of questions on the chat.
Should I look at the chat myself?
Yeah,
I can read
I'm
it
kind
out.
of thinking I seem to be a little bit short of time. So if there are any questions that are important to be asked right now, please just ask them. And if not, we can kind of postpone them to the end of the talk.
Right.
All right. So, so once this worked out, we asked ourselves, can we do better? And this can we do better is coming from a very kind of simple, obvious observation that contiguity is a little bit of a kind of, I don't know, downer. So I'm here in a context like this. I really care to group the right and read of X together, because that would be the thing that gives me the power to reorder it against the other right and read. But somehow there is, based on the bad luck of the observed run, that read of Z is appearing in the middle, and I'm only letting myself pick contiguous grains. So I have no choice to kind of include that read of Z into this grain. But the moment I include it, now the two grains do not commute, because commuting them would break thread order. So in a sense, I would lose even before I start. And instead, if I could just pick, the other side as a grain and leave that read of Z out, I would have actually things that commute. I mean, you can kind of, as humans, see here that read of Z has nothing to do with that grain. It can move up, and then these two grains would commute against each other, as they would for two contiguous grains. So this kind of gave us the idea of what we call, in contrast to contiguous, scattered grains. Wouldn't it be wonderful if I was not doomed to only pick contiguous subboards as grains, but any subboards that would be, useful to me? And I want to kind of make a quick observation that with the scattered grains, when it's a case like this, that the thing that you are kind of picking a grain, the blue one, picking another grain, the pink one, and now you're sort of entering the world that you're breaking this total order business that Deepak asked me about a few times, right? Now I'm kind of looking at a run that is really not totally ordered anymore, because the blue and the pink grain are occurring simultaneously in this run. And I can say that, oh, okay, in the cases like this, when there is really no connection between the two, I can just pretend that it's one of the two situations. The grain appeared before or after that grain. But it's not always like that. Sometimes the other grain would actually be not independent of the other one. Now you have your case, yourself in this kind of situation that we call entangled grains, right? The two grains are truly simultaneous, and there's nothing you can do about it to move it up and down. So maybe this is not super convincing, but there is no other short way for me to kind of tell you that this observation sort of is the root cause that tells us that when we work with the scattered grains for discussing equivalence in the context of concurrency, we are no longer in this pure commutativity-based setup anymore. So, but we are not kind of leaving it entirely. We are very adjacent to it. But exactly because of this complication, we cannot pretend that we are in this world, that we guess grains and then we move grains around and we land where we want to land. Things are a little bit more ugly, let's say. So in this context, if we wanted to decide the causal ordering or causal concurrency based on scattered grains, we need a new mechanism. We cannot just, the way that I mentioned to you, translate to Mazurkiewicz up to a homomorphism. And this new mechanism is what we call a grain graph, which is more or less exactly what you expect it to be. You would have nodes for your grains, and you would have edges between the nodes, depending on whether two grains are dependent on each other or not. So for example, whenever I see things like two grains sharing a thread, I would throw an edge. I'm kind of not throwing an edge between those dot, 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 intermediate events, just, because they're dot, dot, dot events, but the idea stays. Like everything that shares a thread would get an edge between the corresponding grains. And then if two grains share a variable and at least, one of them is a right, I'm kind of putting this a little badly and a little simply. The real kind of clean version is exactly what I showed you about soundness, that you want to kind of say that there is a dependency between the two grains because there is the grain has this characteristic that it's sort of stuck compared to the other grain in the position that it is. So for example, this read of y that you see here, because it's sort of entangled in this right of y, read of y in this grain, and as such, it has to observe that right, and therefore it cannot move anywhere back. And then I have the same kind of situation with this read of y and that right of y, imposing an ordering between these two grains. And then once I observe, these things, in the grain graph, I can just say that two grains would be declared causally ordered by the grain graph if and only if they're connected in the standard graph theoretic sense for a directed graph, which means there is a path from one grain to the other. So the pink path that you observe here says G1 is ordered before G4, G4 is ordered before G3, and G3 is ordered before G2. And you kind of would think that, okay, we are sort of done. You have a grain graph. You have seen, many of you maybe graph algorithms like this before, that you would see immediately there is an algorithm. Let's wrap up this talk quickly. But there are a bunch of complications that I want to point out that we had to fix to be able to actually have a constant space streaming style algorithm based on this notion. So the first one is not exactly a complication, but an observation that is important. That the scenario that I showed you before, if you look at the grain graph in this case, you will see that the grain graph is cyclic, right? Because there is an ordering between these two events for this kind of thing. Oh, actually, I meant that to be a right. I think I made a mistake here. Please ignore this and imagine that to be a right. And then you will see that there will be another kind of ordering here. The point is that this kind of scenarios can happen. The grain graph can actually have cycles in it. It's not really reflecting a partial order as our instincts in this area usually wants to take us. And this is really not a problem. The only thing that we have to be kind of careful about is that as such, the grain graph is defining a quasi-order, not a partial order in the standard partial order sense. But this is not a problem otherwise. Still, we maintain the fact that this grain is ordered before, that we won't call these two grains concurrent, and this grain is ordered before this, and this grain is ordered before this through exactly that path, okay? So this is not a complication, just an observation. But the complications start when we start to kind of think, okay, if we were to implement an algorithm based on the grain graph, of course we cannot maintain the grain graph the way that I defined it. Of course, I cannot have the entire grain graph, one node per grain, no matter where the grain appeared way in the past in the graph, because that effectively becomes the lower bound linear space kind of memory, which I'm trying to avoid. So I need to not have to maintain the entire grain graph and only a very small part of it. And unlike the case of contiguous grains, I have challenges. For example, when I have contiguous grains, there is always at most one grain that is sort of open, that I'm in the middle of. Whereas if you have scattered grains, as this kind of diagram shows for you, you can see that you can be at a point that you can have an arbitrary number of grains that are active or open. So you have, I sort of decided to pick this really degenerate, let's say, case of grains that these rights and these right read of X and this right read of Y in the other thread become a grain. But then I'm sequencing these shapes back to back, and you will see that at this dashed line, all these grains G1 through Gn are active. And you can kind of acknowledge immediately that I can make this to be any number that I want, proportional to the length of the run. And this won't do, because at the very least, I have to keep track of active grains, even if not all grains. And I need a bound here. And we can immediately make an observation that we really don't need to consider grains like this, that there is a way to make canonical choices about grains without giving up anything in the original definition in terms of declaring causal concurrency or causal orderedness. In this particular case, we kind of call this a choice of minimal grains. So we say that it suffices, or it's complete, to only choose minimal grains rather than all possible choices of grains. And the concept of a minimal grain is basically a grain that cannot be further broken down without us compromising its commutativity properties. So if you look at G1 through Gn on the left, and if you look at the variations, G1x's and G1y's on the right, you will see that the ones on the right effectively have much better commutativity properties than the ones on the left. So whatever the ones on the left were supposed to do for me in terms of declaring causal concurrency and basically predicting a race, the ones on the left, the ones on the right would do as well and better for me. And then I'm not getting into the details, but it can be proven without that much trouble that you can always choose minimal grains this way by breaking down bigger grains into this sort of minimal choices. There are canonical choices. And more importantly, if you only choose minimal grains, the number of active minimal grains is always bounded. It has nothing to do with the length of the run. Such a number has to do only with the number of threads and the number of variables. And as such, we kind of get ourselves to a point that we say that, okay, if the grain graph were to only keep track of active grains, we are back into the constant memory RAM. But that's not the only problem. So let's kind of identify the other problem. So if you look at this picture that I showed you before, you will see the problem that I'm trying to kind of talk about. Here, the train G3, the grain G3 kind of has a really long lifespan, which can happen with the scattered grains. It's really active, really mostly throughout this example. But the trouble that it's causing is that for me to observe that G1 is before G2, in the order of the things that I see in a streaming fashion, I would only establish it when I see the last pink edge. But think about when that last pink edge comes. It comes at a point that G2 itself is gone. More importantly, G4, by the time that I want to establish this edge, has ended, because G4 sort of ended here, and then I saw the rest of G3 coming, including this read, and I wanted to establish this. So in some sense, we call this problem the retroactive paths problem, that if I were only to keep active grains, there are these paths that would form retroactively between active grains and somehow grains that have already ended and are long gone. And we need to correct for this to be able to maintain connectivity precisely as the original completely full-on grain graph would do. And to cut this short, we can do this. There is this notion which we call summarized grain graph. The main key is that you only keep track of the active grains and the source and destination grains in addition to active grains. So for example, if I care about grains G1 and G2, they will always stay. And beyond that, I will only maintain a node in this graph for an active grain. So now I know that the number of nodes in the graph is always bounded, but I need to maintain connectivity as the original graph would. And for this, I would sort of always transitively keep track of connectivity as grains die. For example, when I observe a thread order kind of edge between this and the next grain, and that grain becomes inactive, I sort of let that edge be kind of borrowed by or inherited by the next one. And when I, then I see the other edge, which would stay, has nothing to do with the summarization, then this grain would die and I let the next grain inherit it. And now comes the point about the second interesting aspect of a summarized graph beyond like maintaining transitive connectivity. And that is when G4 is about to die, I can maintain connectivity to what? G4 is not really connected to anything else. It's about to die, and I'm about to basically lose all future connections to it. And this is the point that we sort of borrow a trick from something that I did years ago, like, when I was looking at complex realizability and monitoring for complex realizability. And that is the idea of letting the original grain sort of inherit the contents of this grain that is about to die. So we sort of say that G1 now, because it's connected to a grain in the future that has a right Y, when that grain is about to die, but G1 is the one that is staying, it's a predecessor of it. Now we say that we pretend G1 is actually making a right Y. So when that future read Y comes, and that grain G4 doesn't exist anymore, it doesn't have a corresponding node in the graph, the connectivity that would get through it would actually now be, there through its memory in G1. So now we establish the actual orderness between G1 and G2 in this summarized graph through this basically set of tricks, keeping track of transitive edges and merging the contents of the grains that are about to die into their predecessors so that their future connectivity can be done to their predecessors that are still there and living, and therefore overall connectivity in the graph is maintained. All right, so almost done. To summarize, with these tricks, we can basically argue that based on a summarized grain graph, we can have a single pass constant time algorithm that would monitor based on scattered grains as well. And those are the two tricks that we needed to basically bound the memory of this to make it actually constant space. And we have, we can kind of argue, even if not based on anything, based on the simple dumb example that I showed you that motivate this, that being able to choose the scattered grains gives you strictly more power in terms of prediction and equivalent, declaring the equivalence class compared to contiguous grains. But of course, every scattered grain is also, every contiguous grain is also a trivial scattered grain. So this, in some sense, is strictly the most general version of an almost, but not exactly, commutativity-based a notion of equivalence that we can define around the run and decide causal concurrency based on. And if I were to just take a minute to kind of tell you where things stand with respect to this kind of as a research direction in general, if you've noticed throughout the talk, I really never gave you a clean algorithm. Every time I wanted to argue for you that this is doable, I sort of wave my hands and says we use non-determinism and because non-determinism is a power there that exist in, classic automata, we know that we can use it to still argue for this. But of course, all this non-determinism when it comes to actually implementing an algorithm has to be determinized and resolved. And maybe we're constant with respect to the length of the run, but we can have potentially terrible complexity with respect to all the constant factors, which is the number of threads and the number of shared variables in terms of resolving all this non-determinism. So what we're doing now is we're actively looking into first whether non-determinism can actually be resolved efficiently without compromising anything, and then leaving as an option a way of forfeiting some of the completeness to kind of curb down the blow up from non-determinism to actually have a practical algorithm based on this for something like race detection. And then, of course, causal concurrency is a useful generic oracle, but it's really one of many, many uses of where equivalences on runs have been used in verification, in program reasoning in general. A lot of it is in verification. I'm sure most of this audience has heard about partial order reduction, which is use of Mazurkiewicz equivalence in model checking and in, what happens if I wanted to use larger equivalence classes in that context. There are different decision problems, there are different concerns. It's unclear whether the results from causal concurrency immediately generalize or we need to kind of solve these problems based on the same exact notions of equivalence, like grain equivalence or scattered grain equivalence again. But of course, we don't also we think that we have put one point down in this spectrum between easy and hard, and there may be kind of opportunities for further relaxation, but maintaining good algorithmic properties. So it would be interesting to study where the limits of such things are. Where is exactly the point at which you can kind of maintain, for example, constant checkability for causal concurrency, after which you would basically give up and become as bad as reads from equivalence. And yeah, and with that, I'm kind of happy to take questions about everything that I talked about today. And thank you for inviting me again to give this talk.
Thank you, Azadeh. A very interesting talk. Any quick questions from anyone?
I have a question, but it may not be quick.
Yeah, sure, go ahead.
Okay, so when you were defining this one thing where you say that you were lying to us, which was the part where you're talking about in reality the grains may not commute and because of what happens afterwards. It's so am I right to understand it somehow seems like some sort of a mile-narrowed relation where you want to say that two grains can commute if and only if for all words by which you can extend it. The extensions of both those so if you consider the two grains G1 and G2, consider the first trace where it's first G1 then G2 and in the second trace where it's first G2 and then G1, then you say that they are equivalent if and only if for all words by which you want to extend them. They are also equivalent. One trace is valid if and only if the other trace is valid.
I strictly don't want to do that. Right? This is really the point that I was trying to make here. If I take exactly what you mentioned, then the answer of what is that commutativity relation would be the two grains would commute only if their individual bits would commute, event by event against each other. So that, it sounds a little counterintuitive, but I promise if you think about it for 5 minutes, you will arrive at the same conclusion. That if I really quantify universally on all contexts, then basically I'm saying I have to be prepared for anything. And I'm back to the only sound commutativity is the one that, standard Mazurkiewicz commutativity as I defined it would give us. There's nothing more I can do. So this is why I strictly don't want to do this. If I do this, I'm basically saying, forget about grains, just do the classic thing event by event, and that's the best you can get. If I wanted to actually take advantage of the power of grains, I need to leave myself the wiggle room of saying, I'm going to optimistically go ahead and say the context is going to be all right. And only give up if I see that the context is not all right. Then in the cases that the context is all right, I would let myself move things around. And in the cases that it's not, I will just give up that choice.
I see. I was actually trying to think what you would do in case there are liveness properties that you want to check. So these things are okay in this fashion if you want to check safety properties, right? You look at the prefix and you decide.
I haven't thought about this super deeply to give you a confident answer, but I think what you have to understand is the context itself is a safety property, right? The context is really rather simple. If I've decided these two blue grains commute, it means that I'm not going to see a read for a write that appears in either grain before I see a write. So it's kind of like a super simple safety property. I see the read, I give up. I see the write, I declare success, and I don't care about what happens after. So you're mixing, in some sense, in my mind, you're mixing safety for this and liveness of whatever you're checking. So I'm not 100% confidently, but my instinct tells me it's not going to be a problem.
I see. Okay, thanks. I'll think about it.
Sure.
Do you use this equivalence to do some downstream analysis, and is this helpful equivalence that you're establishing in terms of greens to do some useful downstream analysis?
What do you mean by downstream?
I mean, some useful like dynamic analysis of some sort where you want to
like race, like data race detection.
data
Right.
detection
So this is, you know, in a sense, this what we are really actively working on now to have a low overhead monitor for detecting races based on exactly this scheme. You know, there is the ingredients that I showed you help quite a bit. For example, the concept of minimal grains help quite a bit, because if you just select, you know, guess minimal grains as opposed to guessing all grains, makes a huge difference in a lot of cases in terms of how much guesswork you're doing. But fundamentally, success of a monitor is about, you know, the difference between like 5% or 15% overhead, right? So if we want to really deliver on the data race detection, we need to make sure that in, you know, almost every context, we either know that the overhead for the complete case is not going to be too much, or be ready that as things are getting bad and the monitor is getting heavy, to give up a little bit of completeness or prediction power to kind of gain back efficiency. And the degree of non-determinism in the kind of non-determinism that I mentioned to you really highly depends on how many threads and variables you have. So if, for example, you were testing a program with, I don't know, 15 threads, and you were just to completely blindly just guess grains, this gets bad very quick. So what I'm trying to tell you is that the algorithms that I presented to you in this talk are proof of concept algorithms that says there exists a constant space algorithm. It's not something that I advocate someone implement immediately. And implementation requires care, which we are at the moment actively trying to put into this.
So one last question. So do you also have some bounds on the grains you might see given a program statically in terms of source? Can you statically say that, okay, these are the grains that are possible, or like, do you have a number on some metric size of the program or something?
So I think I understand where the intuition behind that question is coming from, a little bit like the concept of transactions, right? In transactional memory, or you know, in deciding things like atomicity, that somehow there are these natural boundaries that would come from the program text for this. I think the intuition doesn't really quite translate here, because really the reason that we are giving ourselves the power to guess all grains is we are like desperately looking for an option that would commute better than the baseline. So I don't really think that the code boundaries would immediately present to you the options for commutation, because if you really think about commutation, it sort of depends on locally what you have in it. Like the less ingredient you have in a grain, the better chances of its commutativity. But then at the same time, how much commutativity it presents, it's sort of like a global question, because it all depends on what else is out there against which this is supposed to commute. So imagine you have a thread that somehow is mostly working independently from the rest of the concurrent program because it's doing some cleanup job somewhere. It's not really interacting. You can pick like ultra long grains in that, if you know, in the pieces of code in that thread, because you know it's not going to have any overlap with anything else. But on the other hand, I need this information, right? I need that sort of non-interference information to be able to pick these grains. I can't be really quite sure of this, but I think not just in this context, from a lot of research that I've done in terms of using commutativity in verification, in safety verification and liveness verification specifically, you really cannot predict what is going to be helpful. And as such, like this power that you let yourself have all the options as much as you know, the complexity bandwidth lets you is super powerful. It may not matter in all cases, but there are, you know, there are like a good number of cases that it makes really all the difference between, you know, success and failure. So that is my kind of long answer to your question.
Okay, so if there are no more questions, let's thank Azadeh. Azadeh, thanks for a great talk.
Yeah, thank you so
Well
much.
done.
If anyone is interested in any of this, please, you know, students and anyone else, please feel free to get in touch with me. I think there is a lot to work on in this context and very few people who are doing it. So if someone has really is feeling inspired, we would be definitely open to kind of talking more about this.